Hello everyone, I'm Marco Toldo, a PhD student from the University of Padua, and today I will present our work about unsupervised domain annotation in semantic segmentation via orthogonal and clustered embeddings. First, a couple of words about the general context in which our model is applied, that is semantic segmentation, where the goal is to provide a semantic label to each pixel of an image. Deep learning had a strong impact on this field, outperforming traditional approaches. In particular, fully convolutional networks are commonly used based on an autoencoder structure, where the encoder generates compact feature representations and the decoder processes them to obtain dense segmentation maps. However, the advance brought by FCNs comes at a cost. They require a large amount of training samples to avoid overfitting, and at the same time, they usually retain low generalization capability. To overcome those issues, domain annotation comes into play. We would like, in fact, to exploit knowledge from a label-abundant source domain to a label-missing target one. The standard approach is to perform a domain distribution alignment of data representations, which can be introduced at different stages within the segmentation pipeline. In this work, we focus on the less explored and more challenging feature-level adaptation, commonly addressed by adversarial techniques. However, adversarial adaptation, in its standard form, tends to ignore semantic modes, providing a global alignment which neglects class-conditional distributions. Thus, we devise lightweight, non-parametric modules looking for class-conditional adaptation over the feature space. We introduce a clustering force to group feature vectors of similar semantic connotation. Then, an orthogonality constraint forces space-out features to be orthogonal, and a sparsity objective is used to suppress weak activations. Finally, an off-the-shelf entropy minimization loss drives features far from decision boundaries. At the core of our adaptation strategy stands the clustering objective. The effect provided by the loss minimization is twofold. First, feature vectors from the same class, but different domains, are tightened around class features centroids. Second, features from separate classes are subject to a repulsive force, moving them apart. As a result, we group feature vectors of similar semantics from both domains into tight and well-separated clusters. We further regularize the latent space by means of the orthogonality and sparsity losses. The orthogonality objective is an entropy minimization loss over a similarity distribution between feature vectors and class centroids. Features from either domains, by different semantic classes, are forced to be orthogonal. Features sharing semantic classification are instead pushed to show high similarity. The sparsity objective further encourages a lower volume of active feature channels. The sparsifying action is applied on class centroids, with an indirect influence over all features from the same class. All combined, clustering, orthogonality, and sparsity modules provide a semantically consistent feature-level domain alignment. We evaluate our approach on two widely used synthetic-to-real adaptation benchmarks. In the first scenario, we consider the GTTI and Cityscapes datasets. We compare our model to several state-of-the-art methods, which, similarly to us, resort to a direct or indirect form of feature-level regularization. The table on the right contains some numerical results in terms of mean intersection over union, computed over a Cityscapes validation set. Our method brings a strong improvement with respect to the source-only training, as well as to the other competing approaches. In addition, our method in general leads to less noisy and more accurate segmentation maps, even on more difficult classes such as sidewalk, bus, or traffic sign. In a second scenario, we change the synthetic dataset to Cynthia. Here, the regularizing effect of the entropy objective proves to be strongly variable. The combination of all modules actually provides a remarkable boost over both the entropy and feature-level modules alone, praising our final approach as the best performing one. Again, we observe that our adaptation leads to a better detection of smaller objects, as well as an improved understanding of the scene layout. To conclude, in this work we propose a novel feature-level unsupervised domain annotation framework for semantic segmentation. As regards our main contributions, first we apply feature clustering to semantic segmentation, then we introduce orthogonality and sparsity objectives to force a regular structure of the embedding space, and finally we achieve state-of-the-art results on feature-level non-adversarial adaptation on two widely used benchmarks. Thank you for the attention. Here you can find some useful links and contacts.